Woo! All right, ladies and gentlemen, welcome back to section 4.1, day 2 notes, where today we're talking about a very important topic, the idea of a critical point or a critical number. Okay, so a critical point is a point in the interior of the domain of a function f. I'm going to pause right here because this is a really key point for some stuff that you're going to have to do later on your own. And that is that a critical point cannot be an endpoint. So critical point is in the domain somewhere. If you have brackets or just a singular bracket for your domain somewhere, whatever that value is cannot be a critical point. So, anyways, what is a critical point? A point in the interior of the domain of a function f at which the derivative of f is either 0 or does not exist at that point. So, critical point, a point in the interior of the domain where the derivative is either 0 or it does not exist. Okay? So, why does a critical point matter? Well, let's take a look. Here is the graph of the same function that we looked at in the 4.1 day 1 notes, where we were talking about absolute versus local extreme values. Okay? And what I want you to do is I want you to take a look at these 3 points down here, the points at C, E, and D. Now, on the graph, these are already marked as a local maximum, a local minimum, an absolute maximum. Remember, absolutes are also local maximums, okay? And look at the derivative at all of these values. And what do we notice? At C, the first local maximum, we have a horizontal tangent line. That means the derivative is 0. At E, we have a horizontal tangent line. At that local minimum, the derivative is 0. And then that absolute maximum, right, up there, the derivative does not exist. We call that a corner. You can go back to section 3.2 where we talked about differentiability, right? And that is clearly a corner there. Okay, so what can we say about critical points then, right? Extreme values are going to occur at critical points, right? Derivative is 0, there's a maximum. Derivative is 0, there's a minimum. Derivative doesn't exist, there is also a maximum again. Okay? And this brings us to the single biggest idea probably in this entire chapter. Okay, because we're looking for extremes, right? Like we talked about in the day 1 notes, maxes and mins. Those extreme values are only going to occur at critical points and, like we talked about at the end of the 4.1 day 1 notes, endpoints. Extreme values only occur at critical points and endpoints. Okay, so if we go back and look at our endpoints at x equals a here, right, we had an absolute minimum there. And then at x equals b, the right endpoint, at that point there, we had a local minimum, right? Look at this graph from A to B, right? Where are all of the maxes and mins? They're either at a critical point, a place where the derivative is 0 or does not exist, or they're at an endpoint, like A and B on this graph, right? Everywhere else, right? Pick any other point on this graph, right? Pick any random point, right here, that point, right? Is that a local min? Nope. Is that a local max? Nope. If it's not a local, then it's not an absolute, right? Pick another point, right? Right here. Does that look like a maximum? Nope. There's points bigger than it right nearby. Is that a minimum? Nope. There's points smaller than it right nearby. Okay? The only places you get extremes are critical points and endpoints. This is a crucial idea for this entire chapter, okay? Because we've done a lot of stuff with graphs, but what we're really going to start looking at is, hey, here's an equation, find all of the maxes and mins for me, okay? And that's exactly what we're going to do next. So let's scroll down to example 1, and we are tasked with finding the absolute maximum and minimum values of the function f of x equals x to the 2/3 power on the interval from -2 to 3. Okay, so how are we going to do this when we don't have a graph? Well, one option is to draw a graph. And actually, we have seen the graph of x to the 2/3. Again, go back to your section 3.2 notes if you want to see that. We're not really going to focus on that right now, okay? So let's talk about how we can find maxes and mins. I have a 4-step process that I like to go through in finding a max or a min. Step 1 is always establishing what is the domain of the function we are looking at. And a lot of you are going to be upset with me, but this is a step I want you to write out, okay? Even when it's obvious, right? You're like, obviously the domain of, x cubed is all real numbers, right? That's okay. If it's obvious, it shouldn't take you long, all right? And on a question like this, where it's like, what's the domain? Well, I don't have to worry about the domain of the function because we're given a specific domain that we want to find the absolute max and min on. And that is -2 to 3. So before we do anything after this, okay, let's talk about this domain. So this domain is a closed interval, right? Because I start at a bracket and I end at a bracket, okay? X to the 2/3, right? Anything here that I can't plug in, any x values that make this not exist? No, right? This graph is going to be continuous. So I'm looking at a continuous function over a closed interval. So what does that tell me? Real quick, alarm bells should be going off in your head if we go back to section 4.1 day 1 notes from yesterday. We talked about the extreme value theorem, the money back guarantee. If f is continuous on a closed interval, a to b, then f has both an absolute max and minimum value on that interval. Guaranteed. So that's going to be a very nice hint for us. Okay, so we know without having to do anything that we're going to have an absolute min and an absolute max, no matter what. Okay, so let's go about in our quest to find this. So that was step 1, establishing the domain. Okay, let's do step 2 now. Step 2, I'm going to shorten this up and I'm going to write CN, short for critical numbers. Okay, so a critical number versus a critical point. This is something that people tend to struggle with. Here's the difference, right? When we talk about a critical point, it's exactly what it sounds like, a point, x comma y. I need an ordered pair, okay? Critical number, I'm just focusing on the x coordinates. So that's what you're going to see me do, is just focus on the x coordinates for now. So let's find critical numbers. Critical numbers occur when the derivative of the function is equal to 0 or does not exist. Now, before I can do that, I first have to find what is the derivative function. So let's come back up here, x to the 2/3, and we do a little power rule. And so we get 2/3 x to the -1/3 power. So that's a pretty easy derivative for us, right? Little power rule there. And now, what I'm actually going to do, and this is one of the reasons why in the past I've not been a big fan of negative exponents, I'm going to rewrite this without the negative exponent because I think it's going to make the next part easier. So 2/3, now x to the -1/3 means x to the 1/3 power in the denominator. So what's x to the 1/3 power? That means the cube root of x. Right? Rational exponents. Okay, I actually prefer it to be written without a negative exponent because of what we have to do now, which is now we have to set f prime equal to 0, and we have to set f prime equal to does not exist, and now we have to solve. Okay, we have to solve both of these equations. So if I take this fraction and set it equal to 0, right? If I want this fraction to be equal to 0, let's think about it. How can a fraction be equal to 0? Well, if I want a fraction to be equal to 0, I need the numerator to be equal to 0, right? But my numerator here is a 2. There's no variable there, right? It's a constant. It's always 2. So can that numerator ever equal 0? No. And so I'm going to write none from there. Now, how can I make this derivative not exist? Well, again, my derivative is a fraction. How do I make a fraction not exist? By making the denominator equal to 0. So how can I make this denominator equal to 0? What x value can make this denominator equal to 0? Well, I have a cube root of x there, right? If x is 0, then that's going to give me 3 times 0, which would make the whole denominator 0. And so x equals 0 is my only critical number. And that's step 2. Okay, so a lot of people like to go from here and then they like to just start answering the question. But we cannot skip step 3. Step 3, probably the most important step. I'm going to come over to the right here because I don't think I have enough room down there. Step 3, I like to call the extreme step, because this is where we're going to determine, is my critical number going to give me an extreme value? Now here's the thing, not every single critical number is going to give you a max or a min, okay? And this is something we'll talk about later on. But here's what we're going to do. So in order to test to see if my critical number gives me an extreme, I'm going to use something called the first derivative test. Okay, so here's how the first derivative test works. I'm going to take my critical number and I'm going to split up my domain into 2 pieces. And so this is going to give me the piece -2 to 0 and 0 to 3. These are not ordered pairs, these are intervals. And now what I'm going to do is I'm going to test and see what is the value of the first derivative in each of these intervals. Okay, so I make a little table here, and now I'm going to label f prime. All right, so here's what we're going to do now. My first interval is -2 to 0. I'm going to pick any x value between -2 and 0. It doesn't matter, it can be a whole number, integer, decimal, doesn't matter as long as it's in that interval. So I'm going to pick -1. And now if I take -1 and plug it into f prime, all I'm concerned about here is, do I get a positive or a negative? I don't actually care to evaluate f prime at this x value. So I'm going to take the cube root of -1, which is going to be a negative. If I multiply it by 3, I still get a negative, and 2 divided by a negative is still going to give me a negative number. Okay, do the same thing from 0 to 3. Pick any x value you want between those. I'm going to pick 1. And now let's take 1 and plug it into f prime. So if I plug it in here, the cube root of 1 is a positive number, times 3 gives me a positive number, 2 divided by a positive number is going to give me a positive number. Okay. And now what I've established here is between -2 and 0, f prime is always a negative number. And between 0 and 3, f prime is always a positive number. Now here's what I want to do with this information. I want to now talk about the function f. So we're not really trying to graph f, right? But what I'm going to do here is I'm going to think. Let's look at the first interval again. If the derivative is always negative on an interval, so let's close our eyes real quick and let's imagine. Think of a function where the derivative is always negative. So think of something simple. How about a line with a negative slope? How about an upside down parabola, and we look at the right side of it? Think of a function where the slope is always negative, right? Where is that arrow going? It's always going down, right? And open your eyes, and that's what f is going to be doing. If f prime is negative, then that means f is going down. F is getting smaller, right? That's what a negative slope does. It makes the graph go down, decrease, get smaller, however you want to think about it. Sorry, real quick, I'm going to change the color on this. There we go. Okay, and now let's think about where f prime is positive, right? If the function has a positive derivative, right, what does that mean? Well, that means it would go up, right? So over my two intervals, f is going to go down and up, right? Now, if you remember my analogy from the last section, what did we talk about? We talked about peaks and valleys, right? If your function is going down and then up, you're creating a valley, right? And what's at the bottom of that valley? That's going to be a local min. So at x equals 0, we have a local minimum. That's what the first derivative test tells us. Okay, when the derivative goes negative to positive, that means the function is going down and then back up. That creates a local minimum. If the derivative were to have gone positive to negative, that would have created a local maximum. Okay, now the reason it's a local and not a global or absolute, right, is because we have to test the endpoints here as well. Okay, and now this is step 4. So step 4, what we're going to do is we're going to test everything out. Move that box down there. Okay, so in step 4, we are going to, and this step, I've never been able to think of a good name for this step, but what we're going to do is we're going to take our two endpoints, we're going to plug them back into the original function. We're going to take our critical number where we know there's a local min, and we're going to plug it back into the original function, and then we're going to compare all of these y values, all of these outputs of the function f. So let's start with f of 0, because that one's easy. What's 0 to the 2/3 power? That's going to be 0. That one's not hard. Okay, let's take the endpoints, f of negative 2. So x to the 2/3 power. If I take negative 2 and square it, I get positive 4. And now to the 1/3 means cube root. And so I get the cube root of 4. And now let's pick the right endpoint, which is 3. And let's do the same thing. Plug 3 into the original function. So 3 squared is 9. And then to the 1/3 power means I get the cube root of 9. Okay, so now absolute max, absolute min, that's what we were tasked with finding, right? So let's see what they are. What's the biggest out of my 3 outputs? It is going to be the cube root of 9. And what's the smallest of my 3 outputs? That's going to be 0. Okay, another way of kind of determining that your local is going to be the absolute here is we actually can look at this and say, you know, hey, my function's going down then up, right? So when it hits that local min, right, there's no other alternative here, right? If we're only looking at this from negative 2 to 3, You know, again, domain is very important here, right? If the function goes down and then up, you know that local min is definitely going to be your absolute min. Okay. Okay. So, let's recap. Step 1, what's the domain of the function? Got to start with the domain. Step 2, we need to find critical numbers. So first we find a derivative, and then we solve two quick equations. Set it equal to 0, set it equal to does not exist. You have to check both, right? Get your critical number. Critical numbers should always be in the domain. If they're not in the domain, they are not critical numbers. First derivative test, we are going to split up our domain at that critical number, check the derivative in each of those domains, and then what we're looking for is sign changes. If the derivative goes negative to positive, like it did in this example, that gives us a local minimum. If the derivative were to have gone positive to negative, we would have created a peak instead of a valley. That would have given us a local maximum. And then step 4, right, we have to check all of the y's here. Check all of the outputs, and then we can determine what is the absolute min and what is the absolute maximum. All right, so let's do this again. Let's take a look at example 2. Find the extreme values. Now I'm going to pause right here. This one does not say absolutes. So this means absolutes and locals. So we'll have to end up with kind of 4 answers, maybe more by the end of this, okay? Find the extreme values of f of x equals 1 over the square root of 4 minus x squared. Now, before I do anything, I know I'm going to have to take the derivative of this, so I'm actually going to rewrite this with a negative exponent because I think it's easier to take the derivative of it that way. But for solving, I actually think it's better to be written without a negative exponent. But we'll get to that when we get there. Okay, so 4 minus x squared, there's a square root in the denominator, so that means it's to the negative 1/2 power. Okay, so we'll come back to this when we get to step 2. All right, so step 1, what's the domain? So, got a fraction here, can't let it equal 0 in the denominator. So what is going to make this equal to 0? 4 minus x squared. So if x is 2, it'll equal 0. If x is negative 2, it'll equal 0. So let's take both of those as the start and end of my domain, and we want to exclude those. Okay, because in this case, right, we don't want the denominator to be 0. So no brackets here. So that means the extreme value theorem is out. Okay, so good with the domain. Step 2, critical numbers. So let's take f of x. Let's find its derivative. I have it rewritten. So f prime of x is going to be, I can use the power rule, negative 1/2 times 4 minus x squared, and now take 1 away from the exponent, so I get minus 3/2, but we have to remember our oldest friend, the chain rule. Multiply by the derivative of what's on the inside. What's the derivative of 4 minus x squared? That's going to be negative 2x. So for taking the derivative, I like writing it with a negative exponent. But for actually using the derivative, I'm going to simplify some stuff. I'm going to rewrite this without the negative exponent. So what's going to happen here? Negative 1/2 times negative 2 goes away. That x is to the first power, so that's going to stay in the numerator. And now negative exponent means in the denominator. So I'm going to have 4 minus x squared to the 3/2 in the denominator, right? But what does that actually mean? I'm going to break this up. So the 1/2 power, the denominator 2, means I'm going to take the square roots of 4 minus x squared, but all of it has to be cubed. So this is x over root 4 minus x squared cubed. Okay, so there's my derivative, and now I have to set this derivative equal to 0. I have to set this derivative equal to does not exist. And now I'm solving two equations. Okay, so what is going to make my derivative equal to 0? So my derivative is once again a fraction. How do we make a fraction equal to 0? Well, the numerator has to be equal to 0. And so that's going to give me x equals 0. And that is going to once again be a critical number. And now, what is going to make this derivative not exist? Well, I need to set the denominator equal to 0. So what is going to make this denominator equal to 0? Well, we actually already talked about it, right? It is going to be 2 and negative 2. So I'll write plus or minus 2. So those are both critical numbers, right? We should definitely go ahead and box these up, right? Any problems with this? You're dang right there's problems with this, right? Plus or minus 2, not in the domain, right? If it's not in the domain, it is not a critical number. Not in the domain. Okay, so remember, critical number has to be in the domain, right? Cannot be an endpoint. Okay, so 2 and negative 2 are out. Get them out of here. So we have one critical number in total, 0. We're going to use this critical number to split up the domain of the function f, and we will do the first derivative test. So my two intervals are going to be negative 2 to 0 and 0 to 2. Some of you might be wondering, why is he using parentheses instead of brackets? Well, that's because when we're testing the intervals, we want to pick a number in the interval, right? I don't want to actually pick negative 2, 0, or 2. So that's why I am putting parentheses there. Okay, so now I'm going to plug some numbers in, right? So I'm going to scroll back up just to see what we did last time, right? I'm going to pick a number from each interval, right? I'm going to test it in the first derivative, and I'm going to determine whether it's positive or negative, and that'll tell me if the original function f is going up or down. Okay, so I am going to need some numbers to test in f prime and f. So I can pick whatever I want. Negative 2 to 0. Negative 1 is a good number to pick. So if I plug negative 1 into this derivative here, okay? So here's the thing, right? I already know the square root part in the denominator is going to always give me a positive output. And then I'm going to cube it, and that's going to give me a positive output as well, right? And so now, if I plug negative 1 in the top, I have a negative divided by what is guaranteed to be a positive, right? And so that is going to give me a negative number, which means that f is going to be going down. 0 to 2, I'll pick 1. Numerator is positive. And if you don't trust me, you can plug it in. Plug 1 in for x, see what you get in the denominator. You're going to always get a positive number, right? Square root cannot output a negative. When you cube a positive, you're going to then get a positive. Positive over positive. F prime is a positive number, which means that f is going up. So, once again, what does this mean? At x equals 0, we are guaranteed to have a local minimum. That's just from the first derivative test, okay? And now, my last step, step 4, right? I have no endpoints here, so I'm just going to take my local minimum and plug it back into the original function, right? When I plug 0 in for x into the original function, 0 squared is 0, 4 minus 0 is 4, square root of 4, I get 2, and so f of 0 gives me 1/2. Okay, so what do we got going on here, right? This one's a little bit weird, right? Because we don't have an endpoint that we start with or end with, right? So what that means is this graph either has open circles at the ends or it has vertical asymptotes and there's arrows going up forever, right? Either way, what I do know is that there is definitely not going to be an absolute maximum. Okay, that much I know for sure, right? There's no absolute maximum here, right? Look at the shape of your function f. It's going to go down and then up, right? So again, where it kind of starts off, right, there's either going to be like an open circle at the ends, right? Or, it could be kind of going up forever and there's some vertical asymptotes. Either way, there's no absolute maximum. First derivative test gave me no local maximum, right? So local max, I'll just kind of cross that off. There's none there. Okay. I know there's a local min, right? Because we proved that with the first derivative test. My local minimum is 1/2. Okay. But now we have to put our thinking caps on. So what is the absolute minimum? Is there an absolute minimum? Because remember, not all locals are absolutes, but all absolutes are local. Okay, so is 1/2 going to be the absolute minimum here? Well, let's think about it, right? So again, we're starting off at either some type of vertical asymptote, which means we're going up forever, or an open circle. Same thing to the right. We're either going to end at an open circle or it's going to go up forever. Doesn't really matter for our purposes, right? But we're definitely going down and then up, right? That's definitely a valley. And this whole graph apparently is just going to show me that valley, right? So that local is also the absolute min. So this is just like the last one, right? If I scroll back up, right? This is the whole graph, down, up. You're making a valley, right? The graph cannot go any lower than that. So my local was an absolute, and we get the same thing here. All right, so let's take a look at the same idea here, but this time with a very fun function. Example 3, find the extreme values of f of x. And this time we have a piecewise function. So we have two pieces here, 5 minus 2x squared when x is less than or equal to 1, and x plus 2 when x is greater than 1. Before we do anything with a piecewise function, the first thing I want to do is talk about that point where the two pieces break off, x equals 1. Okay, I gotta figure out what is happening here. Okay, so the first thing I want to check and see is there continuity at x equals 1? So how do we check for continuity? Right, well, first I need to see if the limit exists, so I'm going to check the limit as x approaches 1 from the left of f of x. So from the left means plugging it into the piece where x is less than 1. So 5 minus 2 times 1 squared is going to give me 3. And now do the same thing from the right. So limit as x approaches 1 from the right of f of x. So 1 plus 2, that is going to also be 3. So that's good. So that is going to tell me that the limit is going to exist there. I'm going to move that down. Okay, so I know now that the limit exists at 1. That's good. And now what's the definition of continuity? I need to check and see if the limit equals the value of the function. So what is f of 1? Well, the equal to is on the piece where x is less than 1. And so that was the left-hand limit, which was 3. And so far, off to a good start, because value of the function does equal the limit. So continuity is confirmed. This is good. I'm going to put a couple of check marks here. That's good. Okay. So why do I want to check continuity? Well, if it's not continuous, well, what do we know about the derivative where x is not, or where the function is not continuous? That would mean that the derivative doesn't exist If the derivative doesn't exist, that means we get a critical number. So continuity is not a concern here, but now let's check differentiability. Let's check the slope from the left and the right. So now I want to do limit as x approaches 1 from the left of f prime. So what is the derivative from the left? Well, 5 minus 2x squared. What's the derivative of that? Negative 4x. So negative 4 times 1. And so we get negative 4. And now let's check the slope from the right. Limit as x approaches 1 from the right of f prime of x. So the derivative of x plus 2 is just 1. And now these two are not the same. Uh-oh. But this is actually going to be good news for us because this means f prime of 1 does not exist. And that means that x equals 1 is a critical number. Okay, so this is going to matter. All right, so before we do anything with the actual pieces of the piecewise function, we want to establish what is happening at that point where the derivative breaks, okay? Or not the derivative, where the function breaks, right? And that's at x equals 1, and we have just confirmed it is continuous but not differentiable there. If it's not differentiable, that means that it is going to be a critical number for us. Okay, so piecewise function, here's where the fun starts, okay? Basically, what we've done up here, right, these first 3 steps in finding an extreme value, we're just going to have to do these twice. And I know that doesn't sound fun, but we got some nice pieces here we can work with. 5 minus 2x squared. So that piece I'm going to do in orange, right? Its domain is where x is less than or equal to 1. And so that's going to be parentheses, negative infinity to 1 bracket. Critical numbers, first need to establish what is its derivative. Well, we already did that, right? 5 minus 2x squared, right? We did its derivative over here. So we know its derivative is negative 4x. And now I'm going to set this derivative equal to 0 and this derivative equal to does not exist. So solve these two equations for negative 4x. And so what makes this derivative equal to 0 when x is equal to 0? Now we have to be careful, right? Not everything is a critical number necessarily. We have to make sure it's in the domain. And this is very, very important on a piecewise function because you may look at this and go, oh yeah, the domain of the function is all real numbers, right? But we have to do this for each individual piece. So x equals 0, right? It is in the domain of this piece, which is good. And so this is a critical number. That is good to know as well. So far we have 2 critical numbers. Okay. So now, how about making it not exist? Well, here's the good news. Anytime you have a polynomial, it is going to always exist. And so that is going to give me none, and I will cross that out. And I know I wasn't doing that before, but you'll see me do this a lot more in the future. I like to cross it out when I know it doesn't give me a solution. Okay, so now, right, what I can do is I can do the first derivative test using just this part of the graph, okay? So x equals 0 is going to split this domain up into 2 pieces. So that's going to give me negative infinity to 0 and 0 to 1. And so now I'm going to pick a number from each of these pieces. I will pick negative 1 from negative infinity to 0. When I plug it into the derivative, multiply 2 negatives, I get a positive. 0 to 1, I'll pick a half. Plug it into f prime, negative times a positive, I get a negative. So what does that tell me? Well, all of that is going to tell me that if the derivative is going positive to negative, then that means I'm going to have at least a local maximum at x equals 0. Okay, so now we're going to repeat the same process with the other piece of this piecewise function, x plus 2. Its derivative is all the values greater than 1. So step 1, all the values greater than 1, parentheses 1 to infinity. Step 2, got to find a derivative. What's the derivative of that? Well, x plus 2, that's a line. Its slope is 1. Okay. And now, same thing, trying to make it equal to 0, trying to make it equal to does not exist. Okay, so now, if I want this derivative, which is just 1, right, to equal 0, is that possible? Nope, not possible. None from there, no critical numbers from that. Can I make 1 not exist? Nope, not possible. None from that as well. So here's the thing. My second piece did not give me any critical numbers. Now, this is actually not a problem. This is actually a very good thing, because now what that means is over this entire domain, 1 to infinity, the derivative is not going to change signs. It's going to be always positive or always negative. We just have to come down here and test it. So 1 to infinity. Pick any x value from 1 to infinity. I'll pick 2. And now you have to be careful here as well, right? You have to make sure that whatever x value you're checking here, you have to plug into the proper derivative. If I plug 2 into the derivative of 5 minus 2x squared, I'm going to get a negative, right? But this part of the graph, 1 to infinity, doesn't correspond with the first part, right? So I shouldn't be using the derivative negative 4x. I need to use the derivative, which is positive 1. No matter what x value I pick, I'm going to always get a positive. And now, what do I know? Well, I know, if I scroll back up here, that we had continuity at x equals 1, right? So I can look at my derivatives across these two intervals from 0 to 1 and 1 to infinity, and I see a sign change of negative to positive. And so that means f goes down and then up, which means it's creating a valley. So that's going to be a local min at x equals 1. Okay, so this time around, I have a local min and I have a local max. Okay, so my last step, no endpoints here, right? Oh, actually, sorry. 1 was an endpoint there. Well, 1 is already my local min, so I have to check it anyways. Okay, last step here is to now plug both of those into the original function. So f of 0, so if I take 0, plug it into the original function, make sure you plug it into the right piece, right? That's going to be up here. So 5 minus 2 times 0 squared is going to be 5. And then plug 1 into the correct function. So again, that's going to be on the first piece here, 5 minus 2 times 1 squared. We already did that. We know it's going to be 3. Okay, so I can safely say that I have a local maximum of 5 and a local minimum value of 3. Those two are guaranteed, okay? But what about the absolutes, right? How do I know if these are absolute maxes or mins or not, right? Because, you know, this is a little bit trickier, right? We have a domain that's going to the infinities. And so one thing you can do is you can try to think about end behavior, right? So let's think about it, right? I know from negative infinity to 0, the derivative is positive, right? So the graph is definitely going up. F is going to go up on that entire interval. But what is it doing as it's near negative infinity? Kind of like if I go to the left, what is it doing? So to help this process along, one thing you can do is you can always just graph the function, okay? Right? There's nothing wrong with graphing the functions, right? And in this case, right, the two functions we have here that make up the two pieces of f are very simple pieces, right? 5 minus 2x squared, That's an upside down parabola shifted up 5 units. That should be a pretty easy graph to make, right? This right here is a point we already know, 0, 5, aka my at least local maximum. And now I'm just going to draw an upside down parabola. And now here I can clearly see that this graph is going to go to the left forever. And so I know right away then that there is no absolute min. Okay. Now, what about absolute maximum? Well, let's keep drawing the rest of the graph, right? Well, I know this graph goes up all the way till x equals 1. And right there, I have the point 1, 3. And now from here, I have my other piece of my piecewise function, which was x plus 2. That's just the line with a slope of 1, starting at 1. And we already know it's going to connect. And so line with the slope of 1, it's going to look like that. And so here's my graph of f of x, right? And now what's happening here? Is this graph going up forever? Indeed it is, to the right. So is my local max my absolute max? It is not. And so I will say none. So feel free to use a graph when you can to kind of help you with the visuals, right? But really, the main thing I was doing here was I was just kind of considering end behavior, right? 5 minus 2x squared, that's a negative even degree polynomial, right? As we go to the left, it's going to go down forever, so no absolute minimum. X plus 2, positive odd degree polynomial. As it goes to the right, its end behavior is up, so it's going to go up forever, so no absolute maximum. Okay. Okay, so that is it for this time, and for section 4.1, I will see you in section 4.2.